Good morning, everyone. I'm here to present my project for this competition, which is titled Freedom in Wireless, a future-proof low-latency wireless microphone system. And here's something I will talk about in the next few minutes. First, I will introduce the characteristic and design trend of wireless microphone system and why the traditional all analog design, the one I hold in my hand, is no longer ready for the future. Next, I will present a novel architecture that is aiming to solve all the issues analog systems have. Then I will go through some implementation details that is innovative and very interesting. And finally, I will give you the future of the wireless microphone system. So let's get started. The wireless microphone system is very different from conventional communication system, mainly in latency requirements and the requirements of continuous signal reception. The latency should be less than 3 milliseconds for live music performance. And also, because the audience are very sensitive to signal drop in audio data, so we should have a mechanism that should reach almost 100% successful reception at the receiver. And the traditional solution is to use a pure analog demodulation. And the system often uses the signal strength, that is, how strong the signal is, to determine whether it is a signal or is an interference. Also, being an analog solution, it has a very limited tuning range. Also, it uses 2 antenna network for each transmitter to achieve higher reception quality. And the design trend of wireless microphone system is twofold. One is spectrum, the other being the modulation scheme. The spectrum become more crowded, and for example, FCC start to auction off 600 and 700 megahertz band. However, pure analog hardware is not flexible enough to cover the frequency range. The other is wireless microphone system starts going to digital. However, pure analog hardware is not possible to modify the existing product to receive digital signal. So here I present my novel architecture. One of the main achievements of my architecture is the complex PL module that to demodulate the data. To demodulate data in the FPGA, and it's a very high throughput, low latency, and economical in hardware. And also, the other main achievement is the centralized baseband management that is incorporated in the system control and management units. And the system management unit use several libraries, like library USB, X11 library to achieve GUI and the remote control network capability. And also use a multi-thread library, so it can run on multi-core CPU ARM and achieve thread-level parallelism. And in the FPGA, I have a high-speed, low-latency demodulation module using complex PAL. Also, we have a FFT computation module that can draw a spectrogram, allow user to inspect which frequency is the least interference burdened. So it can change the frequency of transmitter using a UART, RF, and IR link. Now let's give you some implementation details. I solved the problem of frequency offset by polling the DC offset of the final demodulated data and change those frequencies accordingly. And I pre-processing these IQ samples in ARM using a lookup table to achieve blazingly fast conversion. So in my work, it's not purely software demodulation or hardware demodulation. It's a hybrid design. And next is the main part of this project. It's a complex PAL demodulation module. PAL is a negative feedback loop. If we inspect the feedback path, we can see that this is essentially a voltage control oscillator. A voltage control oscillator is essentially the transmitter, the modulation process of the FM. So by putting a modulation block in the feedback path, we can use negative feedback to construct a demodulation block and achieve very high linearity and superior performance. Also, complex PAO takes two inputs. So in the frequency domain, one of the peaks will be cancelled out. So that gives you a single peak error signal. So we can use a very simple loop design to achieve high performance. And I greatly simplifies this module using the vector rotate IP provided by Altera. And it is very economical in hardware with only 10 cycles delay and very high throughput and very low latency. And here's the MATLAB simulation result. As we can see here, the feedback path, the feedback signal will check the incoming signal continuously. And by using a negative feedback, the phase difference will essentially be the perfect reconstruction of the modulated data. And also, I have a signal. We can observe that the Y0 indicates how similar the input data and the feedback signal is. And it is a signal strength independent indicator. And here's the proof. So by using this indicator, we can indicate that whether the signal is present or the signal is not present and is the noise. So if the signal is present, the feedback signal will track the data input, and the signal indicator will be distinctly larger than under interference. Note that the traditional analog solution will fail here because the interference is too strong. And the other main achievement of this project is using high centralized baseband, which is a very popular architecture in wireless infrastructure. Traditionally, the all-analog solution will fail because interference will be very strong. But my system won't fail because as long as there's one antenna have a good reception, the output will be good. And we have a more flexible system between high reliable and higher channel count. And we have a very good frequency performance, very low latency within 3 milliseconds. And we have a very long range, about 150 meters because of centralized baseband. Now, the future of wireless is going digital. However, because of the bandwidth requirements, there requires a very complex audio compression or source coding, or very complex modulation scheme or channel coding, and only FPGA can do it real time. I show this by modifying the original architecture, the post-processing block, with a clock recovery and decision block, and we are able to achieve the modulation. So, all-analog system only can receive signal like this, and my system can receive signal like this, and it becomes the world's first wireless microphone system to receive analog and digital signal in both VHF and UHF band. So in conclusion, using FPGA and ARM, we can build a platform that is highly flexible, low latency, parallelism, easy to management, and better sound performance, and have a better resource utilization. All because we design an architecture that is closely matched the niche of FPGA and ARM. And we have the freedom, future-proof, low latency wireless microphone system. And it's also applicable to other applications like IoT gateway or testbed for RF engineer or student in education market. And the cost is 1/10 of a similar product. Thank you very much.
Thank you. 谢谢我们